Okay. Good afternoon. Good Friday. Good March day. You can see the board. Right. Today I'm going to continue on shearing stress distribution equations. And we are also going to look at shearing stress for composite material. Term test 2, we will test until here. Okay. Shearing stress for composite materials is very easy, not difficult at all. Okay. Nothing new. Right. So we look at this problem. Okay. I don't want to determine the stresses at point A or point B. We have done that. But rather, we are going to formulate the shear stress distribution equation. Okay. So what we are going to do is we are going to apply what we learned on Tuesday. Okay. So what we learned on Tuesday is we have this set of formula, right? And we are going to apply what we learned over here to derive the shear stress equation. So it's related to our Tuesday's lecture. Okay, so we're going to apply to an actual problem like this. So as I mentioned before, okay, so given the centroid is 35 millimeters from the top. Okay, so I'm going to sketch a green line. This is our centroid. A question like very similar to this will come out for your term test. I repeat again. Okay, a question. So if you look at your homework on shearing stress, how many questions are there? How many? 10. One of those questions will come out and I'll make you derive the what? The stress equation. Which one? You don't know. Okay, but you know there's one that's going to be on shear stress equation. So also given that IZZ is equal to 5.813 times 10 to the power minus 6. So what I mentioned down here, the equation of the shearing stress is dependent on the thickness of the structure, and we're going to form piecewise equation. Okay, so let's look at the cross section now. Okay, so this is our cross section, and knowing that our centroid is 35 millimeters from the top, so this is our centroid. So we are going to form the distribution equation. And this distribution equation, the limits are as follow. The limits will be from 0.015 y, and it will go to 0.035 meters. So the equation we're going to form has these limits. Why these limits? Okay, so we know over here. So what do we know? The centroid is the what? Is the geometric datum. The distance from here to here is what? 35 millimeters. And the distance from here to here is what? 0. What? Or 15 what? Millimeters. So the equation that we are going to form has to be within these limits. Why that limit is because the thickness is equal to what? The thickness controls the limits. I repeat again, the thickness of the section controls the limit. Are we clear? Okay. So from here, we're going to have a variable. So this is going to, so from the datum, this is our y. And then we are going to have a line over here. This distance is going to be our y bar. Okay. So now the equation that we're going to use is shear stress xy is equal to Vy over Izz Qz divided by what? T. We know our Vy, we know our Izz, we know our T. T is over here. We don't know our what? Qz. Okay. So Qz as a function of y, this will be equal to what? Width times depth times by what? Y bar. Okay. So the width is equal to 0.16. The depth is equal to 0.035 minus y. And the next one will be equal to 0.035 plus by y multiplied by what? Half. So this is our width. This is our depth. This expression over here. This is our y bar. You have seen this before. I repeat again. You have seen this before. You have seen this on Tuesday lecture. If we were to go back on Tuesday's lecture, what we have over here is what? If you look at this expression, B bracket C minus Y, C plus Y multiplied by what? By half. Are we clear? You've seen this before. Okay. Remember, when we were deriving this, we were deriving to set the 5 rules. Yes or no? So that is why from here, we realize that we have what? 0.035 because the analysis starts from where? When y max is at its what? Maximum. Are we clear? Then have minus y plus y. Okay. So from here, this will be equal to 98 times 10 to the power minus 6 minus by 0.08 y squared. Okay, let me make sure that this is right. So 0.035 times by 0.035 times 0.5 times by 0.16. 98 times 7 minus 6. And then you have 0.16 times by 0.5, 0.08. Okay. Now it's best at this point, do everything in what? In meters. Okay, so everything in what? Meters. Okay. And from here, once you have this, the rest is very straightforward. Okay. I'm going to copy the whole thing so I don't need to flip pages later on. Okay. So what's left next is just to plug in into the formula, right? So shear xy as a function of y is equal to Vy over Izz Qz as a function of y divided by what? Divided by the thickness. So from here, Vy, we know that is equal to 90 times 10 to the power 3. Izz, for this case, I say it's given, is 5.813. In the term test, it's not given. Thickness, we know is equal to what? Thickness is equal to 0.16. And then we have the expression over here is equal to 98 times 10 to the power minus 6 minus 0.08 y squared. Before I go on, how do we know that this equation is correct or wrong? I'm thinking about a number between 1 to 50. Sorry, 1 to 100. Can someone tell me what's the number? The one get it? I'll give you $20. What's the number on my mind? Hey, who said that? Anyone else? Yes. Guess wrong, you have to give me $2. Anyone? Then whatever amount it comes out, the correct one will get the full amount. Yeah. Good. Anyone else? Listen. Hey. Don't guess. Troubleshoot. When you go to industry, any questions come like that, do not guess, but you ask what? Question. What's the question you're going to ask? Yes. Good. Higher or lower than 50? Then if I say it's lower than 50, what is your next question? Good. You see where this is coming from? We are not from University of Toilet Water. We're from McMaster. Are we clear? We ask the right question, then you lead to the correct answer. Are we clear? This is what we call what? Bracketing. Why am I highlighting this? How do you know that equation is correct? So it should be equal to what? Don't give me certain value.
I mean, like the one that would add this.
Well done. When it's at the terminal, the value has to be equal to 0. Can someone plug the equation over there? Plug in by what? 0.01. 35. It has to be equal to what? 0. Are we clear? Whether you get A, B, C, D, or F in this class is the fact that you know how to troubleshoot your what? Your answer. Not call me from my office. Is this free or is this rotating? Are we clear? Okay, you have to what? Troubleshoot. You understand that? Okay. So if you plug that, can you know someone try? Is it equal to 0? It's equal to 0. So you are safe. Are we clear? These are all the what? All the checkpoints they have to follow. Now, I come down already, okay? So coming back to here, once you plug everything in, you get what? 90. You got 9 point. I got 9. I got I got 9.483 times 10 to the power 6 minus 7.741 times 10 to the power 9 y squared. So this is your what? Distribution equation. And this distribution, the limits is what? The limits is 0 to 0.015 to what? 0.035. Next, we're going to find the next limit. And the limits are controlled by the what? By the width. Okay. So if you look over here, we are going to do now the next sets of limits where we're going to have is now where? So this is the centroid. Right. So the next set of limits is from where? It's from 0.015 to where? To 0. Yes or no? Why? Because it's controlled by the what? By the thickness. So this is 0 millimeter or 0 meters. Y, and you go up to 0.015 meters. Now the thickness is equal to how much? Anyone? Equal to how much? Yes. 0.04. Why? Because you have twice of what? 0.0, the twice because you have your left and you have your what? Right. Are we clear? Yes. Okay? Just stress distribution equation. What do you mean? Did I write that down or no? Okay, so from here, the same thing. Okay, so from here, the same. Now, you have to be careful over here. Now, for this case, we have to be careful. Why? Now we are looking at, so our y variable now is go up to here. Okay, so that's our y. And then the area to consider, this is your what? Let me draw properly. I do apologize. Yeah, the wife always tell me I have to take drugs to come down. So this is the y. These are the area of concern. And then this is your what? This is your y bar. Okay. So we have to be careful because now you have to consider the entire area at the top also, because at the top surface over here, this is your what? Terminal, and this is your analysis direction. So you have to consider the area of the flange. So your Q now, Z as a function of Y will be equal to your QZ of your flange plus your QZ as a function of Y for your what? For your web. Pretty clear. Okay. So QZ for your flange, the width is 0.16.